This is the final talk of the morning session. It's a pleasure to have Pankaj Vishe from Durham University, who's going to be telling us about a two-dimensional delta method and an application to pairs of quadratic forms.
Thank you for the introduction. Thanks for the invitation. It's a pleasure to be here. It's nice to see there's a lot of interest in circle method in India, which originated in a work of Ramanujan. So also nice to be in a conference where a lot of you have heard of the delta method, so that doesn't happen very often. I'm going to be talking about, so you've heard a lot about one-dimensional delta method and has been used in many settings, also for counting points and for subconvex bound and so on. I'm going to present a new version, which is two-dimensional delta method, a two-dimensional version of it, and application to rational points, which is for a pair of quadrics. This is a joint work with Munshi and Lee from UC Davis and Simon Ryden-Meyerson, who is here from Warwick. So I was hoping that our project will be over by now and the preprint will be out, but it's almost done. It's a bit like election promise. Every time I give a talk, I'm like, it will be done next time, but I think we're almost done, so it should be out very shortly. So let me start with the stuff that everyone knows, like application. So I'll start with a bit more general setting first. So I'll take R polynomials, homogeneous polynomials of degree D, defined over n variables. So these are degree D polynomials defined over n variables. And there are of them, and I'm interested in integer solutions, simultaneous integer solutions of these polynomials. So, of course, basic question here is Hasse principle, when does such a solution exist? But I'm gonna go further, which is quite a standard question to consider in analytic number theory. So you've seen like different versions of this counting function. I'm gonna take a smooth counting function, which is better for analytic purposes. So I'll take a compactly supported function, depending supported in Rn, and then I'll take a parameter p, which a lot of people have been calling b, but I like p. That's also a standard one. So I'll define this counting function n of p as number of integer points which are simultaneous solutions of all these polynomials f1, f2, fr. And then I'm counting them in a box of expanding size p. So that is captured in this weight function, omega of x bar over p. And then I'm not only interested in just finding a rational point, but you can ask finer questions. So this was mentioned in Tim's problem session yesterday, for example. So the question is, can you find an asymptotic formula? Can you prove an asymptotic formula or obtain? For this function n of p, as this parameter p goes to infinity. And what is expected size? I think Tim also mentioned this yesterday. So here's a generalization of what you saw yesterday. So roughly you expect, if you have like R polynomials of degree D, then you expect p to the n minus d times R many solutions So this is the expected asymptotic formula. And we are interested in obtaining this asymptotic formula for this counting function for so the question is for which varieties, complete intersection varieties, can you prove this formula? Again, I don't need smoothness here, but I will, for most of the results that I'll talk about, I will assume this extra condition that this system is non-singular, okay? You can think of this as you look at the variety and look at all different gradients on the variety. So unless the point is 0, then all of them will be kind of linearly independent. So this is how you should think of this. Sorry, what? Yeah, at the end it will be much bigger. Yeah, you need n bigger than dr for this formula to be really, for any hope of this formula to be true. Yeah. Thank you. And this kind of Hasse principle is sometimes also called asymptotic Hasse principle or analytic Hasse principle, which will be the focus here. And again, a really famous result of Birch establishes this as long as n is bigger than r times r plus 1 times d minus 1 times 2 to the d minus 1 plus r. So the dependence in Birch's result is quadratic in r and it's exponential in d. So you need a lot of variables. So I'm just going to give slight bit of introduction on what is known. So again, I'm mostly going to focus on the case of two quadrics. So in the formulation that I gave, R is 2 and D is 2. So I'm looking at complete intersection of two quadrics, unless specified otherwise. So Birch's bound translates to needing at least 14 variables. So you're looking at two quadrics, complete smooth intersection. Birch proves asymptotic formula for number of points in expanding box. What should one expect? So conjecturally, in this case, you need, since the degree is quite low, it's not dr, you need at least 6. The conjecture is you should need at least 6 variables for this asymptotic formula to hold. This comes from Brouwer-Manin obstruction. It has improved that as long as you have 6 variables, there is no Brouwer-Manin obstruction. So this is the state of conjecture. Now, quadrics and intersection of quadrics have been really well studied using geometric or algebraic arguments. Their geometry is very well understood, so it's kind of easier to produce find one rational point somehow than find an asymptotic formula. So if you are not interested in asymptotic formula, so just Hasse principle, then it was the result of Collier-Thélin, Sansuk, and Swinnerton and Dyer in '87. They proved Hasse principle even over number field for a pair of quadrics as long as you have 9 variables. And then Heath-Brown improved. They had already strategy for proving 8 variables, but there was a local condition that needed to be checked. And then Heath-Brown proved Hasse principle as long as you have 8 variables. And then there's a very recent result of Molyakov, who was a master student apparently with Collier-Thélin. He removed the assumption of smoothness. So he only needs much more softer condition like irreducibility of variety or something like this. It's a very general result. You can prove Hasse principle, not just assuming smoothness, but for a general class of complete intersection varieties. But these both results that I mentioned don't give you asymptotic formulae. If you're asking for analytic Hasse principle, then the best known result is due to Munshi. At the moment, that needs n bigger than or equal to 19. And then I'll just mention a couple of results which don't exactly come under limit of r equal to 2, d equal to 2. But first I'll mention my result, which is in this spirit. So if you allow for, if you allow for, instead of k equals q, if you're counting rational point over function field where q is odd, then in one of my previous results, I obtained asymptotic formula for a pair of quadrics, smooth pair of quadrics, defined over function field of odd characteristic as long as you have 9 variables. So, so function field we can do better already, and then in a really cool result, if you're interested in Hasse principle for say quadrics, r different quadrics, then if degree is fixed, you can see that Birch needs quadratic dependence on R, and then this was what would be expected would be a linear dependence, and that was achieved by Simon's work in, okay, I don't have the year, but I think it's maybe 18 or something. Yeah. So he made the dependence on n linear in R, which is what one should expect. But then this dependence is better as R grows. That's a better result. And then I'll mention one more connected result. This is the work, my work with my ex-PhD student Matt Northey. From 2021, we looked at 2 cubics, and we managed to prove asymptotic Hasse principle or analytic Hasse principle as long as you have 39 variables. And this is to be compared with Birch's bound, which needs 50 variables. So this was the first known improvement here. Okay, so that brings me to state our current application of the delta method. So again, this is a joint work with Junshan, Simon, and myself. Again, I will dare to say 24. I think it should be out very shortly. So again, we are looking at 2 quadrics, smooth quadrics. Then we prove asymptotic. Whenever I say HP, I mean asymptotic formula of that type. So in this case, it would be constant times p to the n minus 4 plus big O of p to the n minus 4 minus little o of 1. So this is the kind of formula that one needs. And you prove this formula unconditionally as long as you have 10 variables. The system is defined over at least 10 variables. And now further, if we assume generalized Lindelof hypothesis for Dirichlet functions, then you can reduce the number of variables to n equals 9. So if you assume a certain hypothesis, then you can have 9 variables. Unconditionally, we have result for 10 variables. Okay. Let me move on and talk about Of course, the proof is using the circle method. Is this better than the other chalk, or the same? Okay. Yeah, sure. Possibly, yeah. I mean, again, like the minor arcs become kind of same size when n is 9. Yeah, we didn't think of like looking at log savings, but at the top of my head, I can't say. What is full strength? I mean, you need like a t to the epsilon, yeah. No, you need like Lindelof, yeah. Maybe some kind of subconvex bond. But it needs to be like uniform in the conductor. That's the main thing. I think like any saving would be better, but it needs to be, our conductor is growing quite fast, so it needs to be uniform with conductor. Yeah. Yeah. No. Here, this is over Q. Yeah, over function field, we already have the result for 9 variables unconditionally because you already have GRH. So yeah, other than this result, everything is over Q. Okay, so how does one, let me quickly talk about what one can do with a system of forms. So again, I will only work with two forms. So this delta function, delta of n equals 0. This is a function when, now this is a two-dimensional avatar of what you have seen. This is 1 when n is 0, and it's 0 when n is any integer vector which is not equal to 0, 0. So we are detecting when two integers are equal to 0 simultaneously. And then, of course, we can rewrite it as double integral E n dot alpha d alpha. It's just a two-dimensional version of the circle method. And then that allows us to write n of p as a double integral of exponential sum s alpha d alpha. And then we want to get an asymptotic formula for this integral now. So what can one do? So I'm not going to write as the exponential sum for now. So you can do various things. Traditionally, what one does is you have this unit square, 0, 1 square. You write it as a union of major arcs and minor arcs, where major arcs are everything that is well approximated by rationals of low denominator. For major arcs, you have an asymptotic formula for even if the number of variables are small. And over minor arcs, you typically take the absolute value and try to bound this as an error. But this is very wasteful because if you plot this exponential sum, they have high oscillations. So this was the idea of Klosterman, to somehow be able to treat also major arcs as minor arcs by able to use oscillations of these exponential sums around rationals. What can one do? So there are various techniques that I'm not gonna go into. So the first attempt is due to Ritabrata, the one that I'm mentioning, the nested delta method. So this is kind of you're detecting both forms to be equal to 0 using separate one-dimensional delta symbols. But then this method is wasteful if you do it naively. So you do like a clever trick where you first detect f of x equal to 0 using one delta symbol. And then when you're close to a rational of some denominator in that after using that delta symbol. Then you detect f of 2 equals 0, not naively, but then you first put a congruence condition, f of x is congruent to, f2 of x congruent to 0 mod q, and then you only detect f2 divided by q equals 0. So that allows you to lower the total, total kind of modulus that you require when you do Poisson summation formula. So this is roughly 2 one-dimensional delta applications. You can do what we did in my paper with Matt is also a nice kind of trick that we use often in analytic number theory. So you want to bound. Now we don't do any kind of Kloosterman refinement directly, but what we do is we look at the minor contribution of, so we take absolute value of S of alpha, d alpha, and then use Cauchy-Schwarz, which we always do mostly to lower degree somehow. So you do Cauchy-Schwarz and then you bound it by S of alpha on minor arc square. And then the thing is now, if you, the nice thing is now, when you square an exponential sum, this is exactly equal to S of alpha bar, right? So what you can do here, even though you have squared things, absolute values, what this allows us to look at, now that everything is positive, you can just expand out your minor arcs, and then it allows you to look at somehow oscillations of squares of values. These are very, so for a fixed Q, you can average over different values of A, and then instead of taking absolute value, you look at squares of these absolute values, and you use some kind of van der Kolk differencing to get an exact expression for these squares, and you can still get some kind of cancellations from these averages. This is quite a soft trick as well. Then you can use repulsion that you will, I think you will see in full force in tomorrow's talk. This technique by Simon. I mean, I think it is a standard, it is a technique that is known. But so Simon's version was, you look at now, to bound things on minor arcs, you want to get bounds, right, on exponential sums. So you look at product of these exponential sums. And now if you have worked with these quadratic or cubic exponential sums, if you look at an expression of this type, you can rewrite it in a form in which you lower the degree of your polynomial in alpha, and this is only a polynomial in beta. Then you can get, if you get a good bound for product of exponential sums, then both of them can't be small, can't be very big at once. So this kind of gives you a repulsion of values of your exponential sum in 0, 1 square, and I think Simon will talk more about it in his talk. So it's quite a nice technique. And then, how much time I have? Okay. This is the technique from my work, from our function field. So you may try to do Faraday dissection, which is what people have been trying to do for a while, or for 0, 1 square. But now, as you may know, like there is no analog of Faraday dissection that works with what we want, that gives you this exact partition of 0, 1 square in a form, in a way that they are symmetrically placed to be able to utilize these cancellations. So over FQT, I was able to do this, but over using, I started with Dirichlet's approximation theorem, and then I saw that the only way to have overlaps in Dirichlet's approximation theorem is if the centers of these points lie on lines of low height, and then I could parameterize 0, 1 square analog into intervals that are based around rationals of low height. And then the nice thing over function field is you have positive characteristics, so there are not many ways to get intersections of balls. One has to be contained in the other. So unfortunately, that doesn't work directly over Q. So now, this brings us to our result. So I'll give you a version of 2D delta. So I'll start with a parameter Q. Thankfully, everyone has seen one-dimensional delta, so you can compare. So I'll let little delta be any parameter, and Q be bigger than 1. So this delta is not the same as this delta, of course. This is a real number. So a version of the delta symbol says that given such parameter, there exist functions, which I will write soon. So you have this partition of unity, so to say, of the indicator function of 0, 1 square, where you have these kernel functions. So this is an analog of PQ of W in one-dimensional sense. I will, in a second, say what this mysterious object is. So I'll give you exponential sums, a partition of unity of 0, 1 square, where my arcs are basically these smooth functions around each A over Q. Plus a very small error, so now both of them, yeah. I mean, simultaneously the vector should be co-prime to Q. That's it. One component can be co-prime, not co-prime. So where this object AQ, lambda Q AQ is this lattice K times A plus any multiple of Q, where K either integer and Y. So now it's not as nice as one-dimensional version where this only depends on Q, but rather these functions depends on lattices. So they have this symmetry that as long as if I take two different values of A, if the lattices match, then you get the same exponential, same function. And now with extra conditions, that first of all, if you look at this function, when Q is small and W is small, then it is exactly equal to 1 plus, again, a very small error. As long as we can actually make it more precise, as long as Q is less than big Q to the half minus delta, and W is strictly less than 1 over Q to the 1 plus delta. So in this regime, we know exactly what these functions are. They're equal to 1. So this helps you with major contribution. And now we also have following decay property for these functions. So PAQ of W can be bounded. So this is not the best bound one can get. You actually have better information, but I'm not gonna write it here. So you have this decay property for these functions. So if you look at this term here, it's saying that your function is supported in an interval of size 1 over q to the half, essentially. So these are exactly what you would expect if you wanted to use Dirichlet approximation theorem. Okay, so okay, so bunch of comments. So first of all, as I said, these functions, so these are smooth functions. Did I say that? Okay, so of course they are smooth functions on R2. The thing is that these functions only depend on the lattice. So they don't depend on A directly exactly, but they depend on which lattice is produced by that particular A. So in particular, if I take A bar and I take any multiple of A bar, which is where K is co-prime to Q, okay? So if I take A and K times A, where K is co-prime to Q, then if you look at the definition of the lattice, it's easy to see that they'll give you the same lattice. So in this case, you always have this, that A times, so you at least have this one-dimensional symmetry where your functions are kind of symmetric along multiples of Z mod Q Z star. So you have this one-dimensional symmetry, at least in this these functions. So this is what will help us at the end when you apply, Kloosterman refinement. The other thing is also, of course, as I said, the support of P is roughly inside a ball or a rectangle of size 1 over big Q to the half plus little o of 1. Can you guys see it in the back? Or it's a bit small? But these is kind of like what you should expect from Dirichlet's approximation theorem. So you have your functions which are supported in a box of size 1 over Q, little q, big Q to the half. And then the last one that is not intuitive just by why that should be the case, but hopefully I can tell you when I tell you about the proof, is that if you look at this bound for these P functions, then as Q becomes smaller and smaller, when Q is small and W is smaller than 1 over Q to the half, then these bounds are actually growing. So our functions have kind of, at least in a mid-range, you have to expect some kind of growth. So this, which is not the, however, as Q are small and W are small, you are looking at smaller and smaller sets, so it kind of compensates at the end. However, one has to, this adds slight complication, but in the worst possible case, your functions are equal to 1, which is when Q is largest and W is largest. Sorry, as Q smaller and W small. So this is the formulation of our delta method. How much time I have? 15 minutes. Good. Okay, so let me give you an idea of how the proof works and give you at least initial steps, which are kind of easy to explain, where this delta symbol is coming from. So maybe I'll very quickly recall what one-dimensional delta method does. So in one dimension, you want to detect when n is 0, right? You want to detect when integer is 0. The way to do it is to look at duality between two sets. So the thing is, like, if I have an integer dividing n, what does this mean? This means that n can be decomposed as q times n over q. Both of these are natural numbers, if n is natural number. So you have this duality of sets that on one side, I'm looking at all divisors of n. On other side, I'm looking at divisors of n, and I'm looking at dual divisor, n over q. So say everything is over natural numbers. As long as n is non-zero, then we know that, maybe I'll take absolute value, just for the sake, both these sets are equal if n is non-zero. And what happens when n is 0? Then this set becomes all natural numbers, and this set becomes 0, because the dual divisor is always 0. So this duality exactly is broken in this sense, and then you can analytically detect it quite nicely by giving a weight function omega, which is supported away from, because you want to detect the difference between these two situations, and then you do this same game, and you look at, on one hand, omega of q over q, and on the other hand, you look at dual divisor, n over qq, maybe absolute value. And then as long as n is non-zero, both these vanish, so this is 0. And when n is 0, this will vanish because my function is 0 at 0. And then here I'll just get a sum over all q's. So since I have this weight q, to make it delta method, I normalize it by this factor 1 over cq. So this is the really nice picture over for 1D delta. So now I'm interested in some kind of duality in 2 dimensions. In particular, I want to detect whether an integer vector is 0, 0 or not. So again, what would be the duality relation? It's not as, again, when I'll write down, it's not that, it's kind of intuitive, but it's kind of hard to see. This is why nobody has done it so far. So again, we are looking at now, say on one hand, I have all integers dividing n. Okay, so if I have an integer vector n, I can look at all integers dividing n. What does this mean? This means that my n can be written as q times n over q, and there is also an integer vector. So I have this decomposition of type n equals q times r, where this r is also an integer vector. Okay, so this is my dual divisor in some sense. And then how is r characterized? So if I give you an n, then r is a vector such that n is a multiple of r, right? So n belongs to the lattice generated by r. So you have like q is defined by the relation that q divides n. R is defined by the relation that the lattice generating r contains n. So this is my duality relation now. Again, when I write it down, it makes sense. So on one hand, I have q dividing n. On the other hand, I have all vectors in R such that this n belongs to the lattice generated by R, and then I only take non-zero vectors. Okay. Again, these two sets are different, right? One is integers and the other one are tuples. So the duality is not as quick as what we saw before. However, they are very closely related to each other by this relation, n equals q times r. So this set, so this set will be equal to, I look at all r such that n is in lattice generated by r. And now I know that the norm of R will divide norm of n, Euclidean norm. So I look at absolute value of Euclidean norm of n divided by Euclidean norm of R. So there must be a Q that corresponds to this ratio. Okay. So now I will write half here because R plus or minus R give you the same lattice. So you'll get the same number twice. So this is what I mean. And again, here you can do similar thing, and you can look at n divided by q. Okay, so both these sets are duals of each other. So, and now let's just look at one set. So again, if n is, or this is n bar, if n bar is 0, if n bar is non-zero, then these are equal. And what happens when n is 0? So when n is 0, this guy becomes all natural numbers, and here I only get integer 0 because these are dual divisors. Okay, so when n is 0, the second set becomes 0. The first one is everything. So this allows you to, this dichotomy allows you to detect when a rational number is 0, and then somehow you want a bound size of both q and r, so simultaneously. So you could actually play around with this, but this is the optimal one formulation that we use for our application. So I'll define, this is analogous to what I said with one-dimensional delta. So I will take a function, omega 1, which takes value 1 at 0, and omega 2, which is supported away from half and 1, supported away from 0. So I put two different functions. And now I will cleverly use this duality. On one side, I have sum over these dual divisors, which are lattices. So the sum is over R in Z2, and then the relation is that this vector n should belong to this lattice R. And then I will put the weight omega 1 on n over RQ, and then omega 2 will be detecting the size of R, which will go roughly of size q to the half. Again, these are natural choices. And then I'll subtract this all other divisors, which are integers in n, and then n over R was corresponding to q, right? So this is q over q. So this allows me to take q going up to big Q, and then omega 2. So R was n divided by q. So I'm putting, this is the dual expression in both these divisors. And the only thing is that I need to add half here because there are two different lattices that give me the same condition. So this is why that half is 4. And now, again, just by what I have told you, when n is 0, n is non-zero, both these sums are equal. So this difference of these two terms is going to be 0. And what happens when n bar is equal to 0 bar? If n bar is equal to 0 bar, the first guy, because this is 0, right? So n is 0, so I have omega of 0, which is 1, and I just have a sum of half omega 2 over R q to the half. In the second expression, now omega 2 will be 0 because omega 2 of 0 is 0. Okay? So it's kind of doing the same thing as before in a more slightly different way, but it's the same logic. So when n is 0, you just have this complete sum over this lattice of this nice function. So roughly this will grow of size q, c times q, because I'm going up to size q to the half. Okay? So my final expression is going to be 1 over constant times q times the difference of these two terms. Okay? And this is the starting expression that is really crucial to our delta method. Any questions so far? What is little c? Again, c will just come from, this will be equal to the integral of this guy, right? So yeah, because you want something to be 1, you just choose a c such that it becomes 1. Yeah, I mean, you can just write down, this is just integral divided by. Okay. And now, so this is really the main step that, just like in the one-dimensional case, that led to everything. But now, how do you proceed further? Maybe I just have 4 minutes. I'll give you a bit more details. So you have this condition, right? N is, you have these two conditions. I didn't say, sorry. I need this condition that Q must divide N bar. Otherwise, that's not true. So that's the condition, yeah. Just to separate these two functions, omega 1 and omega 2, they have different behaviors. This one detects 0 and this one kills 0. So because like they become 0 at different times, I have two different terms. So I want to keep one and only kill the other one. Okay? You could have done the other way around as well, probably. Again, it comes from how you want to apply it. You can play around with this, yeah. But then at the end, you will need to choose n of certain size and r of certain size, and kind of the way you should think of this, as these r should be thought of as lines, and your rational numbers are lying on this line. If you use like pigeonhole principle, you look at rational numbers of going up to size q, then they have to lie on a line of size at most q to the half. So kind of, there's a canonical choice for this R. So to complement this Q in some sense. I think you can change them around a bit, but then your support will change. And yeah, that's an interesting question. Like what happens if you choose different parameters instead of these ones we said. But this choice gives you the support that we need somehow. Okay, so where was I? Okay, so I have these two conditions. This condition here is nice, right? Q divides N just can be detected by adding additive characters. Yeah, just like what we do in one-dimensional method. This one is slightly more, so when can I, how can I make sure that N is in R? So this has to be a multiple of R, right? So first of all, GCD of R must divide N, right? And the other one is, if I write a R as a GCD times a primitive vector, then primitive vector perpendicular dot N should be 0. So now this is the one-dimensional delta method. So you just have, if I take R perp and take dot product with N, that needs to be equal to 0. So you detect this condition using one-dimensional delta method. What you're really doing is, as it will turn out, as you're kind of looking, it's similar picture to what I said over function field. This is kind of giving you points on this line given by R dot N is 0. So you're looking at rational numbers lying on this line and kind of giving some weight function there. That's exactly what happens. So this is how you do this, and after doing this, you use one-dimensional delta symbol with, say, same parameter Q. And then you will get the following expression coming from there. So maybe it looks, so now I'm fixing R, and I have this weight function over R. And what I'll do, as we do in one-dimensional method as well, you use Fourier inversion to separate this variable n. This is how you get these kernel functions PQ. So I'm going to use first, in this case, the delta method for detecting rpub.n equals 0. And then, okay. Anyway, I'm out of time. I don't know, I can show you later the expression and explain more. I think maybe I'll stop here.
Thank you very much, Pankaj. Does anyone have any questions or comments? Yeah.
So here forms are of same degree. So can you also vary the degree?
Yeah, I think you just need to choose this, the function omega 1, omega 2, they were chosen somehow to only depend on the norm, right? So you can choose, probably choose them to be like of different size, and you can change, you can get like a version of digital approximation with like skewed boxes as well. Yeah, I think it should be possible by playing around with these weight functions in a nice way. Yeah, that will allow you to vary degree later.
Yeah, Sumit.
What is the final choice of Q? What are you choosing Q? So Q in terms of size of n.
Sorry, which Q? This Q?
Capital Q.
Big Q. Okay. Yeah, it will depend. So it will depend on which system of polynomials.
Yeah. So in your theorem,
I think it's 4/3. What is our p to the 4/3? Usually it depends on the degrees of the polynomial that you.
For size of equation, suppose size of equation is n. So what is the choice? If size of equation is n, then
size of
equation is n. Suppose n is varying over interval of length capital N.
How much is Q? Yeah, I think 3/2.
3.
Yeah. 2/3. Yeah. 2/3.
2/3 of
Does it seem correct?
2/3 of
yeah.
n. Okay.
Yeah.
and to compare it with the nested delta method.
It's 3/4.
So there, I think
3/4.
modulus is 3/4.
3/4.
Yeah. 3/4. We have 2/3.
Okay. Thanks.
Any further questions? I have a brief question. So I guess we can use the delta method over number fields.
Yeah.
And I guess you can show that any quadratic form over a quadratic number field has the expected number of solutions using the smooth delta over number fields. And I guess you can do this Veil restriction in that setting, and I guess you could handle quadratic forms in 4 variables over number fields. And when you do the Veil restriction, that would give you a pair of 2 quadratic forms in 8 variables.
Okay.
Which in principle you should be able to get a similar lower bound for, or asymptotic estimate for the number of solutions. So I'm just guessing, I'm wondering, like, what's the most general system of 2 equations in 8 variables which you could handle basically by using the delta method over number fields?
You mean for upper bound or asymptotic formula?
Asymptotic formula?
I think, again, like in generic case, like you do get bounds that work for 8 variables, but then somehow things get quite complicated, and like when your moduli Q is not generic, kind of non-generic, then you kind of run into trouble. So I think it may be possible, assuming some hypothesis for exponential sum. We were thinking about it, but we. I mean,
So what I find if I try the one-dimensional delta method over a quadratic number field, and then interpret it as a two-dimensional delta method over Q, is that the sort of fairy dissection that you get is very, very far from optimal. So I'm going to get this the wrong way around, but your denominator is Q. So some of them are made entirely of primes that are 3 mod 4. And so that denominator is already a natural number. While some of them are made entirely of Gaussian primes lying over primes that are 1 mod 4. And so the absolute value of that that Q is very different to its norm.
I see.
And so in one extreme, the arc around a Gaussian integer, a Gaussian rational with that denominator, has the same size that we have here, so the size that one would want. And in the other extreme, it has the denominator is like way bigger than you want. So if you interpret it this way, what happens is that your denominators, either your arcs are like really big, which causes one kind of terrible problem, or and this is probably the one is going to choose, you'll have to choose the parameters so that your denominators can sometimes be much, much too big, the square of the size that you would like them to be. Which comes from clearing denominators of a Gaussian fraction. So you start off with a fraction where the denominator is the size you want it to be, an absolute value, but then you want to make that denominator a rational number, and so you have to make it twice as big. You have to square the absolute value, and so
yeah. I mean, this is the first thing I tried as well
want.
when we did our number field work. So his comment is like, if you look at number field of degree 2, for example, we have this delta symbol version that works over number field, and you can think of like unit square in number field, the totally real is like R2, right? So it kind of gives you a partition of unity for 0, 1 square already using, but denominators and numerators are now were Gaussian integers, say, or whatever. And you can interpret it as in R2 format. Yeah, as Simon said, yeah, like because you look at norms of ideals, some of them have too big norm, and then that doesn't really work. Yeah.
I actually, incidentally, so I find just because I find this process of trying to use the one-dimensional number field delta symbol as a two-dimensional delta symbol, so you have worked on this and understand it better. I find it very difficult. And so to understand this, I find it useful to consider Getz's gang's recent article on a non-abelian circle method, Arala Getz, Su Li Wang, where so they do this over the quaternions essentially, where so every prime splits in the quaternions if you apply their method in the case of the quaternions, and essentially the decomposition of the unit cube that they're using has like really big denominators, like the denominators Q are like much bigger than you would like them to be. And so if you apply their method to try to count solutions to a system of 4 quadratic forms, then you end up trying to handle exponential sums to moduli that are just way bigger than you would like.
Okay. Thank you, Simon. Any final questions? Well, I think we're done. Thanks very much, Pankaj.
Thank you.